Hi, everybody. Welcome back to Environmental Organic Chemistry with Dr. Lisa. Today I'm going to give you just a short introduction to the chemistry of drinking water disinfection. This is not a topic that's in our textbook, but it's something that I think you really ought to know as environmental people, period. You ought to know a little bit about how drinking water disinfection works. And this is a nice topic to hit right before we start talking about photochemistry, because the chemistry of drinking water disinfection is about electrophiles. So we spent some time talking about nucleophiles in the lecture on hydrolysis, but the chemistry of drinking water disinfection is about electrophiles, and it turns out that the chemistry of photochemistry is also about electrophiles. So this is a kind of a good place to talk about the chemistry of drinking water disinfection. So this is one topic for which there's lots and lots of information out there. The American Society of Environmental Engineers and wastewater engineers has lots of YouTube videos that are intended to inform the public, but they're also used as training videos for people who work in the wastewater and drinking water treatment fields. So these are just a few that I thought were interesting and useful to you. I encourage you to watch them on your own. And some of this information we'll cover, but there's also new stuff in these videos that might be useful to you, especially if you're thinking about going into the drinking water or wastewater field. So let's quickly just review what it is that we do when we create clean, safe drinking water. So we have to have some sort of source of water, and protecting the water source is usually the most important thing that you can do for drinking water quality. Okay, so for example, Adirondack Park in upstate New York was created specifically to protect drinking water and also water for navigation. A lot of the areas of China that are sort of upstream of the big urban areas have been designated as preserves specifically to protect drinking water sources. So that's the most important thing you need to do, is just protect your source water. Once you've done that, then you bring in your source water here, and typically you add some alum. I don't know if you can read that, it's very small, but alum is used to aid in the settling of solids because it changes the pH and causes the solids to flocculate and settle out. So it needs a little time to mix, and you add your chlorine for disinfection here. So you add those chemicals, you let the water mix a little bit to give it some time to react, and then you move it into a settling basin where it's quiescent for a while. That settles out a lot of the solids, which are removed here in sludge removal, and then the water goes in usually through a sand filter or some sort of filter. Then you add some lime to raise the pH. The pH over here is usually on the low side. We want a low pH here. Low. I can write with my horrible pointer. Low pH, and by low I mean 6, 6.5. I'm not talking about a pH of 1 or 2, but then you raise the pH over here because even that mild acidity can cause pipes to corrode. And this is part of what happened in Flint, Michigan. As you guys are aware, or maybe you're not aware, in Flint, Michigan, what they did is they changed the source of their drinking water because they wanted to save money. And the new source, as I understand it, was a little bit more acidic. So they sent that more acidic water out through their pipes. That caused the pipes to corrode. The pipes had lead in them, and so that released lead. If they had stayed with the old source of drinking water and the old process, they would not have corroded the pipes. They would not have created the lead issue. And then we also, in most public water systems, we add fluoride to protect the teeth of our children. If you live in a house that has well water, like I did when my kids were growing up, your pediatrician will give you fluoride drops, like vitamins, for the kids to protect their teeth, but most people live on public water and it gets fluoride. And not actually shown here is that there should be a chlorination step or a disinfection step somewhere here right before the water leaves to provide a residual disinfectant as the water moves through the pipes. So this is really, really important. I cannot stress enough how important chemistry of drinking water disinfection is. So here's just one example. This is the death rates from typhoid fever in the United States, and you can see back around 1900 the death rate was really high, but then around 1910-ish, kind of peaked around 1910, 1908. Around 1910 is when we really started to take this seriously. We learned about the chemistry of drinking water disinfection. We started using chlorine, and when we started using chlorine to disinfect, the death rates from typhoid just fell off a cliff. And now nobody talks to you about typhoid, right? Nobody goes around saying, ooh, I'm worried I'm going to get typhoid, because typhoid is gone, because the chemistry of drinking water disinfection has basically cured this problem. And one of the important things to note is that people who died of things like typhoid and cholera and other waterborne diseases were often very young people. So it's not just old people. Old people had already survived all that stuff. Their bodies kind of knew how to deal with cholera. It was the young people that were dying in really high numbers. And so not only did this save a lot of lives, but it also lengthened lives and increased our life expectancy more than just about anything else. Literally, this is civilization's greatest accomplishment in terms of protecting human life and extending human life. And here's just another example of why that's true. So this is from an article from the New England Journal of Medicine, put out a few years ago, comparing the causes of death back in 1900 with the causes of death in 2010. And you can see that back in 1900, gastrointestinal infections, which is cholera and things like that are caused by waterborne pathogens, was the number 3 killer of people in the United States. Number 3. I mean, that's huge. And now, in 2010, you look at this, it doesn't even appear anywhere. It's not anywhere on this list because we have basically solved this problem. So the drinking water disinfection has been the most important thing that humanity has done to protect human life and extend human life. So the disinfectants that we use, chlorine was the first one, the one that was first developed and first used. More recently, we started to convert a lot of plants over to chloramines, which are a combination of chlorine and ammonia. And there's reasons for that we'll talk about. Then you can also use ozone as a disinfectant. Chlorine dioxide works well. And in short-term emergencies or when you're going backpacking or something, you can carry iodine tablets as a water disinfectant. So we have a lot of options to choose from. Here's ozone, UV, chlorine dioxide, chlorine gas, and hypochlorite. So all these two both kind of encompass the idea of chlorine for disinfection. Hypochlorite, is a salt, and chlorine gas is a gas. And there's safety issues involved in keeping giant tanks of chlorine gas around. You don't want that because of, you could have accidents, but you could also have terrorist incidents where they could blow up tanks of chlorine gas and they could kill lots and lots of people. So typically we prefer to use hypochlorite. There's also ways that you can generate chlorine on site basically using electricity. But they still remain some of the more popular ways of disinfecting drinking water. Again, chloramine, for some reason, is not shown here, but here's chlorine dioxide, UV, and ozone. And you can see they're ranked by some different factors. Are they environmentally friendly? Well, chlorine is really not environmentally friendly. It's a corrosive, nasty stuff. It takes a lot of energy to create it, which means greenhouse gas emissions. So it's not really very environmentally friendly. UV is the most environmentally friendly. Even though you do have to generate the UV light, that takes a lot less energy than it does to create chlorine gas. The problem with UV is that it doesn't last. You generate the UV light, you kill the pathogens, but 2 seconds later the UV light's gone and the pathogens, whatever didn't get killed, can start to grow again. Ozone, fairly friendly, but same problem that it doesn't last. So these are quite effective. You can see ozone, UV, quite effective. Not too expensive. Can have big investment costs, though. I mean, that's one of the great things about chlorine is that it's cheap. Operating costs are cheap, but the problem is they're just not environmentally very friendly, and they have a big problem with byproducts, as we'll talk about in a second. So there's all these trade-offs, and one of the big things that's not shown in this table is that idea of, does this last? If you add chlorine in some form to your drinking water, it will last a while as the water flows through the pipes, whereas UV and ozone just don't last. And you need that residual as the water flows through the pipes, or else you just, even though you chlorinated your drinking water to begin with, by the time it reaches people's homes, it could be deadly again. So chlorine, Cl2, has been used since the end of the last century. This is an old slide. So instead of last century, this should be the end of the 19th century. We're now in the 21st century. As a disinfectant, it's effective and it's inexpensive. So chlorine, when you put it in water, it associates with a water molecule, and it gives you hydrochloric acid and HOCl, which is hypochlorous acid. And the HOCl, the Cl2, and the OCl minus all act as disinfectants. And oddly, we really don't know what the mechanism is. After all of these years of using chlorine, we're not really sure, but somehow they disrupt the cellular processes, and it's a terrifically effective way of killing stuff. And it acts as an electrophile, right? Because chlorine here has an oxidation state of 0. And chlorine is one of the most electronegative elements in the periodic table. It would desperately like to have an oxidation state of -1. So it's desperately looking for electrons. And it tends to find them in the cell walls of bacteria and disrupt their cellular processes. And also it's small. It's a small chemical, so it can move through the membrane of the cell relatively easily and get in there and attack. Sort of gets the Trojan horse, gets inside the cell and can attack inside the cell. So the pKa of hypochlorous acid, is 7.5. And it turns out that although the hypochlorous acid and the hypochlorite are both good disinfectants, the acid is much more powerful. So the HOCl form is the more powerful form. And that's going to predominate here from a pH of about 2 to 6. And that's why I was saying that frequently you want your water, while you're disinfecting it, to be around a pH of 6. And then after it leaves the pipes, you might increase the pH. After it leaves your drinking water facility, you might increase the pH a little bit so that it won't corrode the pipes. And these two together, HOCl and OCl minus, together are termed free chlorine. And so you're frequently trying to target the amount of free chlorine that you have in your water system. Chloramines, on the other hand, are where you take the bleach, the HOCl, hypochlorous acid, and react it with ammonia. And you can have several steps here. You get monochloramine, dichloramine, and nitrogen trichloride. And sometimes people call these things combined chlorine residuals. They have disinfecting power. And the thing that's good about them is that they're more stable, so they stick around for a long time. And that's why they make a really great choice for adding to your water right before you send it out into the distribution system, so that over the many hours, perhaps, that your water stays in the distribution system, it still has that chlorine residual and is still killing the bacteria. And the other great thing about chloramines is that they're less likely to form disinfection byproducts. They still form some, but they're less likely. The problem with chloramines frequently is a problem of public perception because they smell bad. And there's lots of stories of drinking water treatment plants switching from chlorine to chloramines and being bombarded with complaints by their customers saying something smells bad. And this stuff is fairly volatile, so these chemicals can all volatilize to some extent. And when they volatilize, they can react with volatile organic chemicals in the air, and they can create what has been described as a smell that smells like cat urine. And so this is frequently a problem where you have, like if you have a new carpet in your home that's outgassing a lot of VOCs, and then it's reacting with any of this chloramine in the air, and you can get this horrible smell. So you get a lot of customer complaints, but it is very effective and can be a great option. So the big problem with all of these ways of disinfecting water is drinking water disinfection byproducts, DBPs. And there's a whole video on this on YouTube that I really encourage you to watch. It's very interesting and shows you, from the perspective of someone who operates a drinking water treatment plant, what you need to worry about. So their disinfection byproducts are compounds that are formed during these reactions where the chlorine or the chloramine or whatever, even ozone, can react with the naturally occurring organic material, the NOM, and you get all kinds of things formed. One of the most important classes of disinfection byproducts are the trihalomethanes, which includes chloroform. You also get haloacetic acids, right? Halo means halogen. Chlorine is a halogen. So chlorinated acetic acids, also sometimes brominated acetic acids, haloacetonitriles, haloketones, haloditromethanes, and there's just a whole plethora. There's over 300 have been identified. There's almost an infinite number of these disinfection byproducts, and they because if you're using chlorine or chloramine, they're mostly going to be halogenated compounds. And between half and 90% of the disinfection byproducts are unknown in terms of what they are. We don't know what their actual structures are. We just know that they're chemicals that contain organic chemicals that contain halogens. So you can see that on a mass spectrum, and you can get a retention time, and you can see that they contain halogen, but figuring out exactly what their structure is difficult. So there's a lot of stuff out there. We don't really know what it does. All of this may be frightening you and making you think that you shouldn't drink public water supplies, but that's not true. You should trust your public water supplies. They're better for you than almost anything else. Well water can get contaminated by, leaking underground storage tanks and things. So well water's got its problems too. Bottled water is really not regulated at all, or not very much. Very lightly regulated versus public water supplies, which are very tightly regulated. So despite this problem, you should still feel confident that your public water supply is not too bad. And again, remember, the disinfection of the drinking water is protecting you from typhoid fever and cholera and giardiasis, which I can't pronounce, but all kinds of nasty waterborne diseases. So it's still a net benefit to chlorinate your drinking water. You just want to do it in a way that allows you to minimize the disinfection byproducts. So trihalomethanes are one of the most common and important classes of disinfection byproducts. And so trichloromethane or chloroform is a carcinogen. There is a current drinking water limit for trihalomethanes total, the sum of all of them, 80 ppb. And so some of those alternative disinfectants produce a lot less of the trihalomethanes or none at all, which is one of the reasons why people have been switching over to them. So the chemistry by which you form these compounds is a little bit complicated, but it depends on the chlorine acting as an electrophile, right? Because again, in this molecule, the OH is a -1, so chlorine actually in this molecule has a +1 oxidation state, which means chlorine is really, really unhappy and desperately seeking electrons. So when it finds this decaying matter that has things called catechol in it, that's these benzene rings with two phenol groups on them, it will attack those electrons. It says, ooh, electrons, I'm going to go attack, and so then the chlorine attaches, and then you can lose this hydrogen to reestablish the aromaticity. Then you can have a second step where the same thing occurs at the same place. You get now 2 chlorines here, and then you start to open the ring. You break open the ring here, and you get these ketones, which is actually called a ketene. And then those ketenes undergo another step where they attack another chlorine. You get the trichloromethyl group here. And then that can hydrolyze. This is a fairly good leaving group. You remember our hydrolysis lecture, OH comes in here, and then this is the leaving group. So the trihalomethane, in this case chloroform, leaves. It leaves as a carbanion, but it very quickly will get protonated. And all of this same chemistry is happening in swimming pools. So, you can't escape it. It's around you. It's happening in my backyard because I have a pool, which I don't want. Don't ever buy a house with a pool, really. Take my advice, just don't do it, because you like it for like 2 years, and then after that you're like, ugh, I hate the swimming pool. So this chemistry happens everywhere all the time, and this is one of the reasons why the swimming pool smells the way it does. So chloramines are in some ways, they are a better alternative to chlorine. But one of the problems with chloramines is that they cause the production of something called NDMA, N-nitrosodimethylamine. It's a semi-volatile chemical, right? So it's got enough volatility that it can volatilize, but it's highly toxic. It's a suspected human carcinogen. There is now a admissible concentration of 7 nanograms per liter, so that's pretty low. 7 nanograms per liter. If we go back here and take a look at our trihalomethanes, it's 80 parts per billion, which is, I believe, also a nanogram per liter. So this is lower. This is a lower drinking water standard than for trihalomethanes. That's the maximum admissible concentration of NDMA. There's not an MCL for NDMA in drinking water, at least not when I made this slide. I should go back and check and see whether there's been a new one that's been introduced. But at high doses, it's a hepatotoxin. Hepatus is your liver, so it's toxic to your liver, so it causes fibrosis of the liver. The induction of liver tumors in rats after chronic exposure to low doses of NDMA is well documented, so not good. It's also turned out recently that Zantac has been pulled from the shelves. You may have heard this because it was contaminated with NDMA. As Zantac sits around and starts to decay over time, it forms NDMA. So it's a problem not just in drinking water, but it turns out that NDMA is present in a lot of other things. There are also other big sources of human exposure: tobacco, chewing tobacco, bacon, and other cured meats, so salami and sausage, beer, fish, cheese, some toiletries and shampoos, cleansers, interior air of cars, household pesticides, and it can form in the stomach after you've already ingested the food during digestion of food or drugs that contained alkylamines. So NDMA is kind of all over the place, and so the argument is, well, yes, there is some NDMA in the drinking water, but that's dwarfed by what you might get from your diet. But on the other hand, I don't smoke. I rarely eat bacon or cured meats. I don't drink much. I can't eat fish. I'm allergic. So, I might have a low exposure to NDMA, and my drinking water might be the main source of NDMA for me, whereas for other people, they have all these other sources. So it's a balancing act to decide whether NDMA is a reasonable compromise, given all the good things that chloramine can do for you. So I just wanted to point out again, NDMA has been in the news very recently. This is just from April 1st, which as I'm recording this is a week ago. In future years, you'll say, wow, that was a long time ago. But as I'm recording this was last week that the U.S. Food and Drug Administration announced that it was going to ask manufacturers to withdraw all prescriptions and over-the-counter ranitidine drugs, which is, Zantac, which is for heartburn, because NDMA can form. It's determined that the impurity in some ranitidine products increases over time, and when stored at a higher than room temperature may result in consumer exposure to unacceptable levels of NDMA. So my understanding is that this is still a really big topic of research in the wastewater and drinking water field to try to understand where the NDMA is coming from and whether there are ways that you could continue to use chloramine but minimize the amount of NDMA that's formed in your drinking water. So that's just a really short introduction to the whole concept of drinking water disinfection so that you as an environmental scientist will know all about it, because you should know all about it. And after this, we're going to move on to talking about electrophilic reactions. So again, this was kind of a nice introduction to photolysis and electrophilic reactions. And notice that the chlorine and the chloramines that we're talking about have to be generated by people, usually electrochemically or somehow. They have to be generated by the input of energy, because naturally occurring electrophiles are quite rare. When we talk about photolysis, we'll talk about how those electrophiles are generated by the influence of sunlight. So that's the inflow of energy that creates these electrophiles. All right, so see you on the other side.